Alright gang, here we go. This is for Chem 2 Unit 8. We're talking about units of concentration. This stuff, a lot of it should be reviewed. Not terribly hard math, especially if you made it this far. You're pretty used to dimensional analysis, being able to convert units, so on and so forth. So this should be pretty easy stuff here. So we're going to talk about these 6 units of concentration here. And they kind of all have their purpose. Alright? But it's important to be able to use all of them because they all have their own different uses. All right, first one, mass percentage. We've kind of talked about mass percentages already way back last semester, but essentially mass percentage means out of 100. Okay, so you take the ratio of the mass of the solute to the total solution mass. Okay, so it's mass to mass, and you're comparing the mass of the solute, or the thing you care about, over the total mass. So it's like finding your score on an exam. You take the score you got divided by the total score times 100. All right, so that's your mass percentage. Very easy. All right, let's try one. Maybe. Go. Okay. Calculate the mass percentage of sodium chloride in a solution containing 1.5 grams of sodium chloride in 50 grams of water. So the mass percentage would be the mass of the solute, which is the 1.5 grams of sodium chloride, divided by the total mass. So the total mass would be the solute, or the solvent, excuse me, plus the solute, 1.50 grams. All right, so you get 1.50 and then times 100 because it's a percentage. All right. So you get 1.5 divided by, calculators are hard, 1.5 divided by 1.5 plus 50. All right, and times 100, so I got 2.91%. 91%. There you go. So the answer for that one is D. Easy enough. All right, and you can work this one on your own. It's really not that hard. Commercial bleaching solution contains that percentage. What is the mass of sodium bicarbonate in that many kilograms of bleaching solution? So essentially, you just have your 3.62 is equal to X over your total solution. So this would be 2,500 because this is in kilograms. And then, yep, times 100. Yep, so divide by 100, multiply by 2,500, you're done. Next two, parts per million and parts per billion. These are abbreviated as ppm and ppb respectively. So essentially we're saying how many parts by mass is our solute compared to the total mass of the solution. So you can almost think of it as the same as mass percent, only parts per million instead of its parts per 100, which would be percentage, it's really parts per million. So instead of multiplying it by 100, we multiply it by 10 to the 6 because that's a million, right? 1 and then 6 zeros. All right, so this would be the formula for parts per million. And then parts per billion, same idea. It's just per billion, so we multiply it by 10 to the 9th because that's a billion, 1 and then 9 zeros. So that's not too bad. These are really, really useful if we're talking about things that we worry about, even the smallest concentration. So lots of poisons, so on and so forth, like stuff like that. Or we worry about the parts per million, parts per billion, or like aerosols and stuff like that. Worry about really, really small concentrations of these things. All right, next guy here, we've talked about this one briefly before. Mole fraction. Okay, mole fraction is the ratio of moles of a substance to the total number of moles in the solution. All right, so moles of the thing you care about divided by the total moles. So it's almost exactly like the mass percentage, right? But we don't multiply it by 100 because it's a fraction, not 100, not a percentage. All right, so this is the mole fraction. Moles of the component plus the total of all moles in your system. Molarity we've talked about before. Okay, we did quite a bit with molarity. That's moles per liter, right? It's right here, moles per liter, right? So the unit anyway, and then molality is this new thing here, and it's moles of solute per kilogram of solvent. And this is wrong. So this is molality. There we go. And so molality is it's very similar, but it's slightly different. Instead of having liters of solution in the bottom, we only use kilograms of the solvent. All right, so this is a little bit different of an experience. So molarity is moles of a solute divided by liters of solution, okay, liters of the whole solution. But then molality is moles of the solute divided by kilograms of the solvent. So make sure you keep these straight. Lots of students struggle with keeping these different, or keeping these separate from one another and distinguishing between the two. You'll see lots of people doing just liters of the solute appearance or solvent up here and so on and so forth. Molarity is always a capital M. Molality is always a lowercase m. You'll also see it written as kind of a cursive M, kind of like that for your molality. All right, so calculation of molality, let's do one of these. All right, we'll skip that one. Practice exercise 2. What is the molality of a solution made by dissolving 36.5 grams of naphthalene in 425 grams of toluene? All right, so molality is the moles of the solute, okay, divided by kilograms of the solvent. All right, so we've got the kilogram of the solvent. The solvent is the one we have more of, so it's got to be the toluene. All right, so that would be the 0.425 kilograms. All right, but we need the moles of the solute. Well, they give us grams, so to find the moles of naphthalene, we'd have to divide by the molar mass. Right, so 36.5 grams of C10H8. All right, and then down here we'll put the molar mass. All right, so this would be grams to moles. All right, 1. Okay, so we've got 10 carbons and 8 hydrogens. Add those guys up. So 10 times 12.01 plus 8 times 1.01. All right, so I got 128. Oh, maybe I should write this in so you can follow. 12.01 plus 8 times 1.01. All right, and this is parentheses. Anyway, so I got 128.18. So we put 128.18 down here. All right, so we take our 36.5 divided by that answer, and we get 0.2476 or so. All right, moles. So we'll take that value, we'll throw this in here. Notice that I'm not rounding for sig figs here because that's not my final answer, and I don't want to round for sig figs early. All right. So we take our 0.247847. I'm writing down the wrong number. 0.28. There's an 8 right here. 0.28476. There we go. Divide that by our kilograms, 0.425, and I got 0.670 molal. All right. So there's your answer there. All right. Let's try one that's a little harder here. Okay. It says the solubility of oxygen gas in water at 40 degrees Celsius is 1 millimole per liter of solution. All right. What is this concentration in units of mole fraction? All right. So millimole per liter. Well, this is really dang close to moles per liter, so which is molarity. So right. So we're just going to be like, well, we have 1 millimole. Well, that's the same as 1 times 10 to the negative third moles. Okay, and we're in liters of solution. And we need to convert this to the mole fraction. Now, just to remind ourselves real quick, mole fraction is the moles of the solute divided by moles in the solution, right? So this would specifically be the moles of the solute and the moles of the solvent. Okay, well, we have the moles of the solute. That's our 1 times 10 to the minus third. Okay, so far we've got this figured out. We're at 1 times 10 to the minus third up top. Okay, and then in the bottom we'll have 1 times 10 to the minus third. Okay, but we need to figure out, and we're going to add to that the moles of the solvent, because this is just the moles of the solute, but we need the whole moles of the entire solution. So we got to figure out, well, what our moles of the solvent would be. Well, we can assume, if we assume that we have 1 times 10 to the minus third moles of our solute, that we had 1 liter of our solution. Okay, so that means we had 1 liter of the solution. All right, and so we can convert this to moles by using the density of water, right? So we know that the density of water is 1 gram per milliliter. So in liters, it would be 1,000 grams for every 1 liter, right? So now our liters have canceled. Okay, and now we're going to convert that to, we need moles of water. This is grams of water. So we'll put grams of water down here, and the molar mass of water is 18.02, and for every 1 mole. Right, so we'll plug that guy in there. So it would be like essentially it's 1,000 divided by 18.02. we get 55.49. 55.49. All right, so that we add that to the bottom here. All right, so 1 e to the negative 3 divided by 1 e to the negative 3 plus 55.49. All right, and I got 1.80 times 10 to the minus fifth. And since it's mole fraction, there's not really a unit for it. It's just the mole fraction of O2. That would be the units on that. All right, so 1.80 times 10 to the minus fifth, so it'd have to be B. All right. Oh, thank goodness that it was. I'd be really confused. I forgot to hit D and E. Good thing it wasn't one of those answers. All right. Okay. This one's very similar to the one we did earlier. You're just essentially changing your mass percentage here into mole fraction and molality. Not too bad. Okay. So why do we use molarity versus molality? Well, the kicker is if we look at molarity, remember molarity is in moles per liter. And then molality is in moles per kilogram, specifically of the solvent, right? Solvent. Okay. So you know that if we take, if we have a solution that's water, right, and we get it really close to the freezing point, water expands as it gets close to the freezing point. So it's going to take up more and more space as it freezes. So as it freezes, the volume of it actually goes up. Okay. So as our molarity as our solution gets closer to the freezing or boiling point, the molarity can actually change quite a bit. However, a kilogram that was water, once it freezes, is still going to weigh a kilogram, right? And water, it's just going to weigh the same because it's the same amount of molecules. Okay, and so the mass itself doesn't change if we change states, or even if we get close to changing states. All right. So that's really the big deal here, is that molality does not vary with temperature because the mass doesn't change. Okay, we're just counting moles in the top, and then we have the mass in the bottom. However, molarity will vary with temperature, especially as we get close to those phase changes. All right. Now the interesting thing is when water is the solute, okay, and we're at like room temperature specifically, dilute solutions. So these are solutions that don't have really high concentrations. The molarity and molality are going to be really close to one another, and that's essentially because when we're at room temperature, the density of water is essentially 1 gram per milliliter, and so those liters and the kilograms of solvent are going to be pretty much the same number. So your molarity and molality are going to be really close to one another. But then as you move, as we get close to the freezing point, then they diverge from one another. And just a final note here, working through all these converting of units, like you can essentially all you want to do is just keep track of your dimensional analysis. Set up your parentheses, figure out what you want to convert from one to another. So you saw me do it in a previous problem, but another trick that I use is to establish, okay, this is what I'm looking for, this is what I'm trying to get to, and then from there move forward. Okay, so that's it for this unit. Nice, short and sweet, or this unit. You wish. Okay, this video here. Okay, let me know if you have any questions, and I'll see you on the flip side.